Hey everyone, I hope you've all survived the first exam. And in this chapter, what we're going to do is we are going to carry on from our discussions of the three-dimensional shapes of molecules. And we're going to add a new little twist to that discussion. So in this first video, what we're going to do is first mostly review different classes of isomers. Okay? We're going to review the cis and trans isomers that we've seen before, and the new thing that we're going to add is some types of isomers that involve chiral molecules. So let's start out by reviewing the types of isomers that we've learned before. So remember what isomers are in general. So isomers are molecules that have the same formula, but they're different. Okay, so they are different molecules that have the same molecular formula. All right. So isomers can come in different categories or different flavors, and these different categories depend upon how those molecules are different from one another. The first type of isomers that we learned about were constitutional isomers, or these sometimes called structural isomers, and we'll review them again in just a minute. Another category are the stereoisomers, and so far we've seen examples of this, which are the cis and trans isomers. So what we're going to add to this are isomers that contain something that we call an asymmetric center, and this is going to make the molecule chiral, which means that it has some type of handedness. Okay, so or in other words, it's like our hands. They look the same, but they're essentially mirror images of one another, and we know we can't superimpose them one on top of the other. Alright, so let's just run through a few slides reviewing some examples of constitutional isomers and some stereoisomers that involve cis and trans relationships. Alright, so constitutional isomers differ in their connectivity of atoms. Okay, so they're isomers first off, so they're different from one another, and the way they differ is how the atoms are connected. So let's just start with three examples here. So here we have butane. All right, and what could be a constitutional isomer of butane? Okay, so one constitutional isomer could be, and we've seen this before, could be this structure here. So we could either call this isobutane, or we know if we follow the IUPAC, this would be 2-methylpropane. Okay, so butane and 2-methylpropane both have the same molecular formulas. So what are the formulas here? So this is going to be C4H10, right? We have 2M plus 2 hydrogens. Isobutane also C4H10. So these molecules have the same formula, but they have a different connectivity of atoms, and so they're constitutional isomers. So what about a molecule like cyclobutane? Is that a constitutional isomer of butane and isobutane? Well, the first thing we'd have to figure out is if it has the same formula. All right, so cyclobutane, what's the formula here? So again, it still has 4 carbons, but how many hydrogens are there? Okay, there's 2 hydrogens on each of those carbons, so only 2, 4, 6, 8. This is H8. Remember, that has an unsaturation, and so this is not a constitutional isomer of the 2 above. All right, so what about cyclo? Here's cyclohexane. Right? Can we think of any constitutional isomers of cyclohexane? Well, we could just draw a few. We could have, say, a cyclopentane with a CH3 on it. All right, that would be constitutional isomer. Still has the same formula. We could have a cyclobutane with 2 methyl groups attached. How else could we make the same formula as that? So remember that the formula of cyclohexane is C6H12, right? And so this has 1 unsaturation. It has 2 hydrogens less than the maximum that 6 carbons could have. So another way to make this unsaturation is to put a double bond. 3, 4, 5, 6. So 1-hexene would be a constitutional isomer of cyclohexane. Right, so we could make all kinds of other ones, right? We could move the position of the double bond. We could make some branches on there, shorten it, all kinds of things. All right, so what about 1,2-dimethylcyclopropane, right? What's the molecular formula of that? So let's see, we've got 5 in the ring, 6, 7. So we have C7. And how many hydrogens? So we have 1 unsaturation, so it's just going to be 2N. So H14. So we could make some different kinds of constitutional isomers here too. We could either move the position of the methyl groups, right? We could put them adjacent to each other. Instead of 2 methyl groups, we could have an ethyl group, right? We could make a bigger ring with 1 methyl group, right? So we could make all kinds of constitutional isomers. So remember that constitutional isomers are compounds with the same molecular formula, but they're different because they have a different order of connectivity of the different atoms. All right, so what about stereoisomers? Okay, so stereoisomers are going to have the same formula. They're going to have the same connectivity of atoms, so each atom is connected to the same other atoms, but they just differ in the 3-dimensional orientation of those groups. All right, so let's look at some examples here. So if we have this 1,3-dimethylcyclopentane, we know that because these 2 positions are tetrahedral, there's going to be an H on each of those as well. All right, and if we start trying to draw this, trying to indicate 3-dimensional orientation of those groups, because it's tetrahedral, we would have to put the methyl and the hydrogen, we'd have to designate them with one of them being a wedge and one being a dashed line. So if I start out putting this methyl group as a wedge, the H would be a dashed line. And then when we do the other position, we have 2 choices, right? We could either have this as a methyl group as a wedge, H is a dashed line, right? We call this cis. If This one is a wedge with the H and the dash line. If we reverse these, if we put the methyl group as a dash line and the H there, this would be called a trans, right? So these two molecules have the same connectivity of atoms, they have the same formula, but those CH3 groups, the methyl groups, have different three-dimensional orientations. Okay? Alright, so this middle one, we could have the same things, right? We could have the OH going up and the chlorine going up, or we could have the OH up and the chlorine back. So those would be stereoisomers as well. And for this next compound, we have this one, which is could be called trans. So like trans over there, right? So let's go back to those. This would be cis, right? Because these two groups are on the same side. And this one is trans because they are on the opposite side. Transoceanic or something. Trans-Pacific. Alright, so with double bonds we have the same thing. If we look at the two alkyl groups, right, here's a CH3 and here's the propyl. These two are on opposite sides of that double bond. So this would be called trans. And so if we take two of the groups on the end, so for example this methyl group and this H, and we switch places, so we have the methyl down here, double bond, and then like this, so the H's are both up here. Now the methyl and the propyl are on the same side, so this would be cis. Alright, so these are some examples of stereoisomers created by cis and trans relationships. Alright, so the next thing we're going to do is we're going to add in a type of stereoisomer that's based upon something called a stereocenter, or sometimes also called an asymmetric center. Asymmetric meaning no symmetry. It's also sometimes called a chiral center. Alright? So I'm going to show you a little video that's going to demonstrate this with models, and then what we'll do is we'll go on and learn how to draw these. Alright, so let's take a look at a molecule of 4 different groups. And let's start with this. This is 2-propanol, right? So let's draw out possibilities here. We could have our carbon chain just like it's drawn, but of course this bond to the oxygen either has to be pointing forward or pointing back. So let's look at the 2 possibilities. Okay, we could have the OH pointing forward, H pointing back, or we could have the OH going back and the H going forward. So what do you think? Are these the same? Right, so what we'd want to do is we'd want to be able to superimpose them. So if we take this molecule and slide it straight over here, the carbon chain will overlap, but the OH and the H will be backwards, right? And if we try to flip this molecule around so the OH and H match, then this methyl and the ethyl will be backwards, right? So these are not the same. So they're different because of three-dimensional orientation. So these are stereoisomers. Alright, so to be enantiomers, they have to be mirror images of one another. So we'd have to redraw these as mirror images. So let's start by redrawing this one. Alright, and what I'm going to do is I'm going to take this structure and I'm going to rotate it around this axis right here. Okay, so we're going to rotate this, and so this ethyl group right here is going to rotate around to this side, right? So it's going to be pointing towards the other molecule. So here's what we would think of as our mirror. Okay, so when I redraw this, carbon chain is like this, right? And when I put that OH on there, is it going to be pointing forward or is it going to be pointing back? Right, so it's going to be pointing forward. Right? So OH, the H is going to be going back. Okay, so I oftentimes think about it like this. If I'm going to rotate this molecule, if I'm just going to flip it over, it's kind of like I'm going to put my spatula under there and I'm going to flip my pancake right over. And so whatever's on the bottom here is going to end up on the top down here. So our OH was on the bottom, so now it flips over and it's on top. The H was on the top, so this is the doughy side. We're going to flip it over and cook that side, so that's on the bottom. Alright, so now let's compare these two across our mirror. So notice that the two ethyl groups face each other. The OHs are both pointing out towards us, so they're reflecting each other. The H's are reflecting, and the methyl groups are pointing away. So yes, these are mirror images, and they're different from one another, and so these are enantiomers. Okay, so they are so enantiomers are stereoisomers that are mirror images. Sometimes they call them non-superimposable mirror images. Okay? And so we could also add something here, is that molecules that have enantiomers are what we call chiral. Okay, so anything that is different from its mirror image will be chiral. So let's look at a couple more examples. Alright, so what about isopropanol, or 2-propanol? That's the one in the upper left. Is this going to be chiral or not? Alright, so let's consider whether it has some stereoisomers. So if we draw it like this, we know that the OH can either go out or it can go back. And we could reverse those. Alright, so we could put the H up here and the OH back here. Okay, so the question then, are these the same or are they different? So let's compare these. Alright, so what do you think? Okay, so these two are actually the same, right? Because all we'd have to do, if we take this axis again and we rotate it around the axis, we get the same thing, right? And so these are what we would call, because their two mirror images are the same, we call them achiral. This means not chiral. Okay? What about the one on the right? Okay, let's look at the possibilities here. Okay, we're just putting this OH here. Okay, so this OH could come forward, or it could go back. The H would go back. Or we could reverse those. The OH is back. The H is forward. Okay, so now we want to compare these. Alright, so let's rotate one of them around to see if they're mirror images or not. Okay, so I'm going to take this one and I'm going to rotate, like I did before, around this axis here by 180 degrees. So that's going to put the OH on the left, like this. Alright, the H was forward, so now the H is back. The OH was back, and so now the OH is forward. So let's compare these two. Right, so those two are mirror images. Okay, are these top two compounds, are they the same or are they different? These two. Alright, those two are different. Right, because if we tried to take this one right here and slide it right over on top of this, the carbon chain and this OH, these would overlap nicely, but the H and the OH would be backwards. Alright, so these two drawings, these two are enantiomers, and either of these molecules we could say is chiral. Alright, because it has a mirror image that is different from itself. Okay, so what's the difference between these two examples? The one on the left was achiral, and the one on the right is chiral. So why is that? Okay, so the one on the right has a carbon that has 4 different groups attached. Carbon has 4 different groups, right? It has an H, it has an OH, it has a methyl group, and it has a CH2OH. Okay, those are 4 different groups, and that is a requirement, or at least it's a, if we have a molecule that has a carbon like that with 4 different groups, then the molecule will be chiral. Okay, this type of carbon is called an asymmetric center. So this is a carbon with 4 different groups. Okay, and when I mean different, it means that they're not the same, right? They have to be completely different. All right, so a molecule that has an asymmetric center will be chiral. All right, but we'll see later that molecules that have more than one asymmetric center may or may not be chiral. So chiral molecules are molecules that are different from their mirror image. Molecule that is different from its mirror image. All right? And the mirror image that it's different from are the enantiomers, and we can call them stereoisomers that are mirror images. Okay? So what do you think? Are these two over here enantiomers? No, because they're the same, right? They're not even stereoisomers. They're just identical to one another. What about these two? We talked about those. These two are enantiomers because they're mirror images and they're different from one another. So not only molecules can be chiral as well, right? All kinds of different things can be chiral. So let's just think of a few chiral objects that we might use every day. All right, things like, well, we said it had to do with handedness, so our hands are chiral, right? If you hold up one hand to a mirror, essentially what you'll see is the other hand in the reflection. Okay, things that go on chiral molecules, chiral items like gloves, right? Our feet are chiral. Shoes that we would put on. Anything else? Okay, a common one is scissors, right? You can have right or left-handed scissors. The desks in the classroom, you know that there's right-handed and left-handed desks. So desks in the lecture hall. Now things like cars, you know, we can have a steering wheel on the right or the left. So all of these things are chiral, right? Because they are different from their mirror images. We can also have achiral objects. Maybe something like a glass, like a water glass or something, or a ball, right? Maybe a chair, right? If it's symmetrical, right? So all of these things are going to have a plane of symmetry. Okay, and chiral objects have no plane of symmetry. Right? That plane of symmetry is if you draw a plane through that object, one side will reflect the other side. Alright, so let's look through a few examples here and just try to decide whether these molecules are chiral or whether they're achiral. Okay? So up to now there's two ways we can approach this. We can either look for a plane of symmetry or we can look for an asymmetric center. Alright, so what do you think about the first one in the upper left? Chiral or achiral? Alright, this one is achiral. Right, because it essentially has a plane of symmetry right down through the middle, so one side would reflect the other side. Also, we could approach this from the point of view of asking whether it has an asymmetric center, and the answer would be no, because it has one group here, one different one here, but then both sides of the ring are the same. Right? So it only has 3 different groups. Alright, what about the next one? We just added a double bond in there. This one is now chiral. Alright, just by adding that double bond, there's no longer a plane of symmetry through here. Alright, what about the next one? Okay, so this one is chiral. Right, here's our asymmetric center, because it has a methyl, it has an ethyl, it has the amine, and it has an H. Okay, 4 different groups. All right, what about the last one in the top row? Sound chiral? No, this is achiral. All right, I'll trick you on this kind of thing, because look, even though this is drawn with a wedge, remember that this is a CH3 as well, and so there's no asymmetric center, all right, because that carbon there has 2 of the same groups. No asymmetric center, right? So be careful, just because there's a drawing with a bond that's a wedge doesn't mean that it has an asymmetric center. All right, what about the bottom left? All right, so this one is, what do you think, is achiral as well. Remember that we could rotate around this, so there would be a plane of symmetry right through here. If we rotate that double bond right into that plane, then it has a plane right down there. And it also has no asymmetric center. Okay, same here. Achiral, right, has a plane of symmetry down through here. What about the last one? This one is chiral, right, because this has an asymmetric center. Okay, when we're deciding if things are different or not, remember they have to be completely different, and that means we can keep going from one carbon out to the next carbon to the next carbon, and they have to be different the whole way. So for this case, we can clearly see that this OH and this methyl group are different from one another, and they're different from these parts to the ring. But if we come over to here, this is a CH2, and this is a CH with a double bond, so those two are different from one another. And so that one is chiral. All right, so that's our discussion on chirality, asymmetric centers, mirror images, and all that kind of thing. So in the next video, what we're going to do, since we can now have enantiomers, we have to have a naming system that allows us to distinguish one enantiomer from the other.